Okay, this video, we're going to talk about the next two things, which are vector operations and applications, and then polar point conversion. Okay, so they're kind of very similar. Vectors and polar point conversions are pretty similar, so we'll be able to do both of them with one swoop. So remember, a vector has direction and magnitude. Okay, so we can have, here's our axis. Usually you put the vector at the origin, and maybe the vector is 5, 9, right? So vectors have things called chevrons, and they're telling you where to go from the origin to this point. So this says go 5 units to the right and 9 units up. So this is our vector representing the vector 5, 9. Okay? And of course, we can always make a right triangle. Right? We can make a right triangle where this is a unit of 5 and that's a unit of 9. And we're able to find the magnitude of the resultant. Okay? So the magnitude of your, basically it's the hypotenuse of a right triangle. And that's exactly what we are finding. When we find the magnitude of your vector, we are doing a Pythagorean theorem problem. We are squaring the x value, and we are squaring the y value, and we're adding them together. Okay? So it's a right triangle problem. We can make right triangles are useful for all kinds of things. 25 plus 81 is the square root of 106, which is like 10 point something. So I don't know what that is. 10.2 maybe would be the length of that vector. So that's the magnitude of that vector. The other thing we can talk about is the direction, which is the angle associated with a positive x-axis. So it's always the angle associated with a positive x-axis. And that's found by doing the inverse tan of the y value over the x value. Okay, so a vector has magnitude and it has direction. So the magnitude is found by doing a Pythagorean theorem, and the direction is found by doing this inverse trig. Sorry, there shouldn't be parentheses here. There should be parentheses, not an equal sign. So if we do this problem, if we put this in our calculator, and we're going to be in degree mode, because we want to know what this is as a degree. My calculator says this is a 60.9 degree angle. So it's about 10.2 units long at an angle of basically 61 degrees. Okay, so that's how you convert and find the magnitude and direction if you're given a vector in basically standard form there, or vector form, chevrons. Right there. Okay. It also could be written in ij form, so 5i plus 9j. Right? That was the linear combination form of that vector. The 5 and the 9 are the same, the x component and the y component. Okay. Now, if we had two vectors acting on a body, maybe we have a 10 Newton and a 20 Newton at 40 degrees. Okay, so usually we would put one of these forces directly along your x-axis. Okay, the first one that they tell you, sorry, it should be the first one that you put. So there's your 10 Newton force, and then you make your angle of 40, and you apply your other 20 Newton force. Okay, and what we were doing in class is we used the parallelogram method to figure out where that resultant would be. So the resultant, or the answer, is going to be down the middle in between your two vectors, your two force vectors. This is your resultant right there. Okay, and what we did was we left one vector, right? This would be the horizontal vector, 10, 0, going directly 10 units to the right and 0 units in the y direction, and we would change our 20 into its component form. So that was the magnitude times the cosine of the angle for the x, and the magnitude times the sine of the angle for the y. Okay, now this is why we're doing it here. Polars are the exact same thing. If you had a polar point, the conversion is the exact same. Okay, we would add these two things together, right? We would get the magnitude vector, and then we would use Pythagorean theorem, just like we did a second ago, to find the length of the resultant, and you would find the angle using the inverse trig. Okay? So that's two things that we would do. Now, that relates to a polar point. So polar points, remember, are given to you with two different values, a radius and an angle. So let's talk about the point, 5 and 60 degrees. Okay, so this polar point on our polar grid has circles, right, radiuses. And for this one, I need to have 5. So we're going to come up 60 degrees. 1, 2, 3, 60 is right about here. And 1, 2, 3, 4, 5. Here is your polar point, 5, 60. So the question is, what is this point as a rectangular? So what is the x, y? Well, we can, of course, make a right triangle out of this because right triangles solve a lot of things. Right? If we can make a right triangle, we can use all of our right triangle values. So there's your x, there's your y. We know the radius is 5 because it's 5 units away from the origin. And we know our angle is 60 degrees. So when we convert this polar point into a rectangular, x is the radius times the cosine of your angle. And y is the radius times the sine of your angle. Exactly how it was a second ago for vectors. Okay, if you're given a vector in its magnitude and direction, you can find the x and the y components. And that's exactly what we're doing here. So when I plug this into my calculator, 5 times the cosine of 60 degrees, right, making sure I'm in degree mode because I have a degree angle, I get a value of 2.5. And when I do 5 times the sine of 60 in degree mode, I get an answer of 4.33. So my 5, 60 as a polar coordinate turns out to be 2.5, 4.33 as a rectangular coordinate. So remember, this is your r and this is your theta. This becomes your x and your y. Okay, so the components are the same. The x is your magnitude or your radius times the cosine of your angle, and the y is the same times the sine of that angle. Okay, vectors and polars are closely related in that they have the same basic conversion formulas. Okay, so that's what you need to have on your sheet, right? How do I convert from a polar point into an xy point? And how do I find the magnitude and direction from a vector into, magnitude and direction from a vector? Okay, hopefully you're figuring that out and will do great on your test.